my name's Reid Draper. I'm super excited to be here. I think I've been talking enough. I'm close to losing my voice already, so we'll see how this goes. I'm going to be talking today about test.check, which is a new closure contrib library for testing. So as I said, today I'm going to be talking about testing, but before I talk about testing, I want to take a little bit of a tangent into performance. And I want you to think for a moment when you have a function or a program whose performance characteristics you're not happy with, what sort of thought process do you go through? What do you do to improve the performance of a function or a program? So let's say that this is the complexity of our function and we want to improve it. We can start playing with constant factors. We can do micro-optimizations on the function. But what we really want to do in order to get the most performance impact is to think differently about the problem and change our algorithm. Oftentimes when you're learning to program, you hear the best performance gains you get are a change in algorithm. And I'm going to claim that with most unit testing and traditional example-based testing libraries, we're kind of in this area right here. We all have our favorite unit testing library, but they're all basic variations on the theme. And in order to get here, we need to think about testing in a completely different way. And I think that test.check is a different way of thinking about testing. So as I said, test.check is a closure contrib library. It is open source. You can get it on GitHub here. It moved to contrib about a month ago, so you might have previously known it as SimpleCheck, which was just on my personal GitHub. And before I dig too much into the details of the library, I want to give a motivating example for the types of bugs that we can find with this style of testing that might not have been exposed before. So we're going to explore a bug that was found in Clojure. Zach Tellman actually found this bug. So here's a simple expression. We're going to create a set. We're going to conj and disjoin some things onto it. And in between, we're going to create a transient and then turn it back into persistent. And you might imagine that this should be equivalent to not turning it into a transient. A transient is just an optimization, right? So these two expressions should be identical. And it turns out we have unit tests for this. How many of you have ever used transients for sets or maps in Clojure? So we have a room full of people who have used this code before, but there's a bug here. These two expressions are not equivalent. So I'm going to show you how we would test for this and find the test with test.check. So with test.check, we think about testing in a different way. We write what are called property-based tests. So you don't have to understand all of this, but basically what we're saying here is that for all actions that we might apply to this set, conjoin this, disjoin this, turn it into a transient, turn it back into a persistent, we're going to randomly generate these actions. So that's going to be bound to A in here. We're going to apply the actions, which is basically just a fold. We're going to look at the action, apply conj, and then we're going to test for equivalence to filter actions, which just removes the calls to transient and persistent and changes conj bang to conj, et cetera. So these should be equivalent to each other, right? And we can run the test. So we've now defined this property. In this case, we're going to run it 100,000 times. It turns out this is a pretty insidious bug, so it takes a while to find it. We're going to pass in our property. And then we're going to get back a result. In this case, the test has failed. The result is false here. And it took 2,800 random tests to find this. This is not a trivial bug that you're likely to run into. And here's the failing case. But it's actually pretty simple. We have a room full of people who have never found this. We have unit tests for it. But taking a different way of thinking about programs is able to find some of these nasty bugs. If you're curious, I don't have time to explain the full bug, but it turns out that 109 and negative 110 have the same hash code, which exposes the bug. So this is CLJ 1285. Like I said, Zach found this. This is still broken in Clojure 151 and is fixed in 1.6. And I've created a little example repository if you kind of want to play around with just this bug. I wrote some traditional unit tests, like 15 unit tests or so, and I wrote a simple property-based test that shows this. So if you want, you can clone this and just type line test and see the bug on your own machine. So test.check has been used to find bugs in Clojure, ClojureScript, and it's used by a few other libraries that you may have run into, Pedestal, Core Matrix. CollectionCheck is the library that Zach made that found this bug. Initially, he was trying to test his own data structure implementations to make sure that they were equivalent to Clojure's. And in the process, decided, well, I might as well test the Clojure data structures too, and stumbled across this fun error. So test.check is based on a library or a suite of libraries called QuickCheck. John Hughes, who's actually in the audience, is one of the original authors of the Haskell one in around 2000. There's also an Erlang one, which John is also an implementer of, that started in around 2006. A Scala one. There's a bunch of other less popular ones, but these are probably the 3 most popular implementations. And in my time in my day job at Basho, I use Erlang, and we use the Erlang QuickCheck, and I do a bit of Haskell as well. So I've been using these libraries for a few years, and as I would dabble in Clojure, I found myself really missing this style of testing, and about a year ago started slowly working on it. And it's kind of finally in a stage that I think it's useful to other people and is finding some pretty nasty bugs. So QuickCheck is based on this different style of testing, which we call property-based testing. You may hear similar terms like generative testing and random testing. But the core concept here is that we're putting constant effort in to get as many individual test cases as we want. So we can write that test as we did before, and then I just put in 100,000. That's how many tests I want. I could change that to 1 million. And I'm still putting in constant effort to get these more test cases. Whereas with traditional example-based tests, for every single test I want, I have to write a new test by hand. And I think this, as you start to use it, really changes the way that you think about testing. So we'll dive into some more detail here. This is a similar property to the one we saw before. In this case, we're going to test that count and concat work together the way that you might expect. So if we concat 2 vectors together, A and B, the count of that resulting vector should be the same as the sum of the 2 original vectors, right? If we concatenate 2 5-element vectors together, the sum should be, or the count of the resulting vector should be 10, 5 plus 5. So we start with this universal quantification, which says for all valid input to this function, this property should be true. Next, we create bindings to something called generators. So in this case, we're creating 2 vectors, A and B. This is sort of like a let clause. We're going to bind A to a vector of any value. So gen any means generate any valid Clojure data structure. Same with B. And then inside the property, for each test run, A and B are going to be bound to randomly generated values of that vector. And then we just return a Boolean. So we're just returning true or false, is it true? So we can run this. Again, we've bound that property to P, let's say. We run it 100 times, and we get a map back, a data structure that represents the result of this test. And unsurprisingly, this test is true. We ran 100 tests, and we actually get the random number seed back. So if you want to rerun the same test with a random number seed, these tests actually are deterministic. And in starting to write tests this way, one of the first problems that you run into is, since it's a completely different style of testing, you have to change the way you think about change the way that you think about writing tests. And this means thinking in properties. As we're going through these, we're looking at our functions and saying, OK, what sort of assumptions can we make about what our function does? And this takes experience, and I think is one of the more difficult parts of property-based testing. But I'm going to go through some common themes that I found. The first one is a round-trip property. So let's test 100,000 cases for Eden serialization and deserialization in just a few lines of code. So we can say for any printable value, A should be equal to printing A and then reading A back as an Eden string. We can do this for JSON, for XML, but it turns out there's other functions that have this types of relationship: zip and unzip, partition and flatten. So if you start to think for a bit, you can start to find these pairs of functions that do something to your data and then undo that thing. And if you run tests like this, you start to find pretty interesting results. Another example is using a trusted implementation. So let's go back to our example here. Transients are just a performance optimization, right? We should be able to test that transients work by applying the same set of actions to a regular persistent data structure and testing against that source of truth. And this is actually the same property that I showed in the beginning. So we're able to test the implementation of transients against the implementation of regular persistent sets and maps, et cetera. The next example, and this one I think is a little bit more ambiguous, but thinking about how the inputs to your function relate to the output. So the example we gave before of the count of the concatenation of two vectors is the sum of the count of the individual ones. We're using the input to describe the shape of the output here. So in order to write these tests, we have to write generators or use generators that are already written. So as I said before, on the left-hand side of these properties, we have the variables that our generators are going to be bound to, and then the right-hand side, we declare what type we want to generate. And test.check comes with a bunch of batteries included generators for all the basic Clojure built-in data structures. And there's a function called sample, which allows you to sort of see at the REPL what the values actually look like. So if we sample a Boolean, unsurprisingly, we kind of just randomly alternate back and forth between true and false. Integers, we generate positive and negative integers. Vectors get parameterized by a generator. Since vectors are collections, we need to know what we're actually generating vectors of. So in this case, we're going to generate vectors of integers. But we could soon enough pass anything in there. We can also sample, in this case, we're just going to take one example because otherwise it would take up the whole slide. But we can generate any printable Clojure value. So in this case, I think we're generating a map where the first key is a keyword, the value is a string, the second key is a list that contains a map. So we can create these really complex nested things. And it turns out in a lot of cases for testing serializers and deserializers, these kind of nasty nested test cases are what you have to generate in order to find some of the more nasty bugs. We also have a set of combinators to create more complex generators from the built-in ones that map to your domain. So we can create person records and such. So the first simple one is basically the constantly of generators. So gen return creates a new generator that always returns the value that you've passed in. So unsurprisingly, we just get foo back every single time. We can also specify a specific range for integers. So genint will generate integers of arbitrary size, but let's say in our domain we only want integers from 5 to 10. In this case, it's inclusive. We can create a generator like that. We can create a generator that chooses a random element from a list. So we can enumerate our values. In this case, we're going to enumerate some programming languages, and then gen elements is just going to choose one at random. One of allows us to do a similar thing, but instead of choosing between different elements, we can actually choose between different generators. So in this case, we're going to randomly alternate between Booleans and bytes. So we see 119 is how a byte gets printed. So these are bytes, and then we can alternate between Booleans as well. We can apply a frequency to that. So 5 out of 7 times we can return weekday, 2 out of 7 we can return a weekend. So we can actually control the distribution of these as well if the default uniform distribution doesn't make sense for our application. We can filter the values. So if we want integers that are not 0, if we want lists that are not empty, we can start to compose these things together. Getting a little more complex, we have one called fmap, which allows us to apply a function to every value generated. So if you sort of think of the list of possible values generated as a lazy stream, we can map over that stream and apply the odd function to every element. So we can go from a sequence of random integers that can get generated, apply odd to it, and turn that into Booleans. So in this case, the function we're passing in is going to return an actual value. Sometimes we might want to take that value and create a new generator. That's what bind allows us to do. So we have a similar shape here. We're passing in a generator, in this case, vectors of integers, ignoring the empty vector. And then we're going to return a new generator, which uses the tuple generator, which is just a fixed length vector, where the first element returns the vector that was just generated, and the second element of the tuple chooses a random element from it. So we take a look at sample of this. In this case, we've generated a vector of -3, -3. Unsurprisingly, we've had to choose -3. An example here, we've generated this vector, and then we can randomly choose one. So this allows us to compose more complex generators together that actually depend on the values of previous generators. Another interesting feature that test.check and some QuickCheck implementations have is something called shrinking. So remember the counter example before of the bug with transients? This is what it looked like. This is pretty simple. We can look at this, and sure, we might not immediately know that these both have the same hash code, but it's not something like this. And you might have been wondering, how did we find this after only 2,800 tests? Well, it turns out we actually found this. This is the original failing random case, and this is hidden somewhere inside of it. So shrinking allows us to automatically start pulling things out and making the input smaller, and continuing to do that until the test starts to pass again. So we can actually do that search that you might, as a human, start to do yourself. If you saw this, you're going to start saying, well, probably all of those actions are not required to make the test fail. I'll pull one out, try it in the REPL, see if it fails. But we've been able to automate that, and this just happens automatically. As you compose the generators together, you get this shrinking built in, such that when the test fails, you get the original failing example, and you get the shrunk case back. I'm not going to go into too much detail into how this works, but the basic idea is that for every value generated, we also create a lazy shrink tree, which represents the ways to shrink that value. When the test fails, then we can start to walk that tree and continue doing so as long as the test continues to fail. So for example here, this is probably too small to see, but the number 8 can shrink down to 0, 4, and 7. So if we run the test and 4 continues to fail, then we can now expand 4 and recursively do this, lazily walking this shrink tree as long as the test continues to fail. We also have built-in support for closure.test. So taking these tests and running them with line test or whatever your favorite test runner is as simple as using this def spec macro. So you just name the property, explain how many iterations you want, and then you just inline put the property in here, and this turns into a test that's runnable with closure.test. There's also a fork of test.check that uses CLJX so that you can use the same code base to test ClojureScript applications. So if you have ClojureScript that you want to test in this way, you can use double check to apply the same principles of property-based testing to testing your ClojureScript as well. So I'm going to talk a little bit next about something that I've been working on and am really excited about. This is still kind of in the proof of concept stage, but I wanted to kind of share it anyway. And that's applying some of these same techniques for testing concurrent programs. And I want you to think for a moment, why are concurrent programs hard to test? I mean, how many of you have had a race condition that you couldn't reproduce on your machine, but your colleague's machine? Well, it works for me. Or it's a Heisenberg bug, and you only get a bug report once a month for it. So why are these programs hard to test? Because their execution is non-deterministic, right? Otherwise, when we apply property-based testing, when I add 1 and 1, I always get 2. The execution of that is deterministic. But when we program concurrently, the execution of our threads is controlled by the virtual machine. And the virtual machine's goal is not necessarily to explore all the possibilities. It's trying to execute things as efficiently as possible. So what if we could make it deterministic? What if we could run your concurrent programs in a deterministic context? So this is work that's based on Pulse, which is also a tool for Erlang. John Hughes is also an author of that. You're probably starting to see a trend. And it allows our property to be, for all interleavings of these concurrent actions, something should hold true. So let's give an example of that. Schedule is going to run this expression inside of our alternative deterministic thread scheduler. So if we create a promise, and then we create 2 futures, the first one is going to deliver true to that promise. The second one is going to sleep for a second and then deliver false. Then we assert that true is equal to referencing that promise. Now it turns out if you just run this in a REPL on your JVM, you're going to get true every single time, right? The virtual machine has no interest in ever making sleeping for a second be faster than just immediately running an action. But in this case, we can all see clearly that there's a race condition here. We're not always going to get true. So what we want to do is be able to randomly schedule the executions of our thread so that we can find those Heisenbugs that most of the time don't surface, but occasionally we get unlucky. And when we do, we have no idea what execution actually caused the test to fail. And when we control the scheduler, we can actually record the interleavings of threads and return that to the user and say, hey, this is the interleaving of threads that I caused to cause this bug. So to kind of visualize this a little bit better, imagine that we have 3 threads, and we might actually have more than 1 core as well. So we might actually be able to run things in parallel. And each thread and each of these dots is going to call some concurrency function. It might swap on an atom, create a new future, deliver a promise. And when we run this under the JVM, we have no control over the execution of this. And once it's done, we don't know what order they executed in. So what we're able to do is, inside of this scope, and I'll explain how this works in a second, we take over the scheduler, and we choose a serial order to run these actions in. And then we can shrink that if the test fails and return to you, I only ran 1 action at a time, and I ran them in this order, and the test failed. Here's the order of these concurrency functions that I ran. You have a better chance of being able to see why the test failed. And if you pass that random seed in, you can actually reproduce the test again. So the basic implementation idea here is that using a function called withRedefsFun, we're able to redefine a set of built-in closures concurrency functions. So we actually provide an alternative implementation of functions like swap, doSync, future call, etc. And instead of calling the normal implementation, we first check with a user-level scheduler thread, am I allowed to run? So we communicate with the scheduler thread, and the scheduler thread sits there and chooses which thread is allowed to run, only lets one of them run at a time, and it records the order that they run in. Then we can return that back to you to see why the test failed. Once the thread has been allowed to run the action, it does actually call the original implementation of that function. It just only does so once it's been told it's allowed to run. So I think that's all I have. You can find test.check on GitHub. The example test that sort of contrasts traditional unit-based testing with property-based testing is on GitHub here. There's going to be an unsession on test.check at 9 p.m. tonight in this room. I'll be happy to take more questions there, go over the implementation, or perhaps help people come up with some properties for their own domain if that's something that you're having trouble with. So thank you, and I'm also happy to take questions now.